Our fascination with the world around us isn't new. We know for a fact that we've been asking questions about what makes rocks and water different for more than 2,600 years. The first known Western philosopher, Thales of Miletus, who is also known as the father of science, conjectured that everything is actually made of water. Greek philosophers developed on this idea for centuries before Empedocles proposed that everything was actually made of fire, air, earth, and water. This was an extremely popular idea, and when this was combined with some sort of concept of a soul, it kept Greek philosophers busy for centuries. Around 2,400 years ago, Greek philosophers Democritus and Lepicus suggested that matter was actually made of indivisible particles called atomos, which is where we derive the word for atoms. But this was not a very popular idea, and despite being accurate, was greatly ignored. Now, today we know that matter is made out of atoms, but there's still a lot that we don't know. For instance, we're still finding new states of matter. Solids, liquids, and gases are not the only states of matter. In fact, we have confirmed over 18 different states of matter. This includes extremely exotic states like time crystals and one-dimensional quantum gases. But what is so different about these states of matter? And what makes a different state of matter to begin with? Let's discuss it. Different states of matter are characterized by distinct quality changes of the material that result from changes in external forces such as pressure, temperature, or electrical currents. These changes are often quite abrupt and are referred to as phase transitions. So what are all these states of matter, and how are they so different? Let's begin with the four fundamental states of matter. These are the states of matter that we see in our day-to-day lives: solids, liquids, gases, and plasma. Most of us are already familiar with these, so I'll be brief so we can move on to the more exciting states. Solids have some form of rigidity, and they form from the atoms being tightly bonded, whether this be in a crystalline structure like diamond or an amorphous solid like glass. Liquids have no fixed shape, and they conform to whatever vessel's holding them. They are formed due to partial bonding of the atoms. The intermolecular bonds hold the liquid together so that it flows rather than separating like a gas. And it is this interaction that gives liquids viscosity. Gases, on the other hand, form because there's either very weak or no intermolecular bonding at all. As a result, there is large separations between the atoms, and thus gases are freely moving and fill whatever space they're in. Plasma is the most abundant state of matter in the universe, and it is an ionized gas. When enough energy is put into a gas, either through temperature or through electrical current, the charges begin to separate. Once these charges have properly separated, this creates a conductive gas or a plasma. Now, plasmas are often forgotten about, but they're actually all around us. From neon signs to lightning, and even the sun itself is made of plasma. But now, let's move to the more exciting states of matter. Starting with one that is actually formed on Earth: supercritical fluids. This state of matter forms from answering the question of what happens to water if we heat it up until it evaporates, and then compress it again until it forms back to a liquid phase. And then we heat it up again and then compress it again, and so on and so forth, until at some point, this process no longer works anymore. Suddenly, there's no distinction between liquid and gas, because a new phase of matter is formed, a supercritical fluid. Now, this state of matter can dissolve solids in the same way that liquids do, but it can also diffuse out of a container the same way a gas can. In this case, supercritical fluids can effuse, which is a particular term to define how a gas can escape a container through a hole that's smaller than the mean-free path. So, a supercritical fluid has the properties of both a liquid and a gas, therefore making it a new state of matter. Generally, this state of matter doesn't form on Earth, but it is predicted to form in gas giants where there's a lot more pressure. But there is one place that we know we can find supercritical fluids, and that's in hydrothermal vents. These hydrothermal vents underneath the sea generate a lot of heat, And this heat combined with the massive pressure of being deep in the ocean is enough to tip the scale to create these supercritical fluids. Now let's talk about some more exotic states of matter. And we'll start with a broad class of states of matter, condensates. All of these states have some form of condensation. This refers to the formation of the lowest quantum state, which in many cases resembles the formation of a liquid from a gas, which has the same name. The first condensate is a state of matter that many of us are already familiar with, superconductors. Superconductors exhibit two main features. They have zero resistance, and they repel magnetic fields, which is also called the Meissner effect. Initially, it was thought that this state of matter could only be formed at extremely cold temperatures. This is because superconductors are formed when electrons form something called Cooper pairs. This effectively changes the electrons from fermions, which repel each other, to bosons that don't. As a consequence, the electrons in this state no longer interact and therefore are able to flow through the material without any resistance. But there's still a lot that we don't understand about superconductors. We have found some superconductors that do work almost up to room temperature, but for all of this to be stable, it requires immense pressure and thus is not practical for everyday use. Hopefully, one day soon we'll be able to find a superconductor that works at room temperature but doesn't require immense pressures. This will certainly change a lot of the way we interact with technology today. So how is this a condensate? Well, superconductivity is all about what the electrons are doing in the material. In a conductor, we can often treat electrons like a gas, with some perturbations due to the atoms and other electrons. In the transition to a superconductor, the electrons in themselves form what's called a superfluid. So while the state of matter itself is a superconductor, the electrons by themselves are a superfluid, and therefore they condense from a gas-like state into a liquid-like state. Talking of superfluids, this is the next state of matter. Superfluids are liquids that have zero viscosity, and this leads to some very interesting effects. For starters, superfluids will climb the walls of whatever container they are in. Normal fluids also do this, but friction stops them from moving very far. Superfluids will also fall through any cracks in the container that they're held in. Even microcracks that were perfectly capable of holding the superfluid in its liquid phase are unable to deal with it once it transforms into the superfluid state. And this is because the superfluid has no viscosity, and therefore the atoms are able to fall straight through these microcracks. And this was a huge problem for researchers that were initially starting to look at superfluids. Additionally, as superfluids have no viscosity, there's nothing to really stop their motion. If you were to stir a superfluid and we removed other external forces, the superfluid would just continue to move, seemingly forever. As you can imagine, superfluids generally form at very cold temperatures. The quintessential superfluid is helium, and this only becomes superfluidic a few degrees above absolute zero. The next state of matter is intrinsically linked to a superfluid. It's a supersolid. This is a state of matter that forms an ordered array just like a solid, but it also moves with zero viscosity, just like a superfluid. Now this is a very new state of matter. We only found this state of matter in 2017. To form this, scientists took what is called a Bose-Einstein condensate, which is another state of matter which we'll get to very soon. They placed this inside a cavity. This enhanced the coupling between the atoms, and this allowed the atoms to form a structured array. And it was this lattice of atoms that transitioned from a Bose-Einstein condensate into a supersolid. Since its discovery, we've actually found many different supersolids, including two-dimensional supersolids. Now, speaking of Bose-Einstein condensates, let's discuss what this state of matter is. For starters, it's extremely similar to a superfluid. In fact, most Bose-Einstein condensates can also be considered a superfluid. And this is because a superfluid is usually accompanied by the formation of a Bose-Einstein condensate. But they are fundamentally different. And not all Bose-Einstein condensates are superfluids. In general, a superfluid defines the macroscopic properties of the material. i.e. that it has no viscosity. A Bose-Einstein condensate, on the other hand, is a quantum mechanical effect. It is driven by the cooling of bosons down to a low enough temperature that they all occupy the lowest energy state. But the difference between the two is one is macroscopic and the other is quantum statistics. Another state of matter is a fermionic condensate. And just like the name suggests, it's formed from the condensing of fermions to the lowest energy state. This often occurs at a lower energy to the Bose-Einstein condensate, and this is because the fermions first have to transition into Cooper pairs before they can condense further into a fermionic condensate. But other than the fact that this is formed from fermions rather than bosons, this is the same as a Bose-Einstein condensate. The next grouping of matter states is Rydberg states. There are two different states of matter that are formed from Rydberg atoms. A Rydberg atom is an atom whose electron has been excited to an extremely high energy state. In this state, the electron orbits the atom at a really large distance, and this allows for some quite interesting physics. Some of this interesting physics is the actual formation of these different states of matter. The first state of matter is called Rydberg matter. This is a collection of Rydberg atoms that form a lattice that are held together by delocalized electrons. Combining these Rydberg atoms into a lattice in the correct way releases the electrons from their orbit. This creates a sea of delocalized electrons. And it is this sea of delocalized electrons that end up holding the Rydberg atoms into place. Now, one might initially think that this sounds like an extremely exotic state of matter that can really only be formed under lab conditions. Well, this may be true, but scientists actually predict that this state of matter may actually form in some locations within the galaxy. The first is halos around galaxies, and the second is deep within the atmospheres of gas giants. We have no confirmation of these states existing in a natural way, but we certainly do have confirmation of being able to produce them ourselves inside of labs. The second Rydberg state is what's called a Rydberb Polaron. A Rydberb Polaron is a state of matter that can only be formed at ultra cold temperatures. This basically consists of a large Rydberg atom whose electron is so far away from the central nucleus that other atoms can sit in between the electron and the nucleus. To form this state of matter, you need to combine Bose-Einstein condensates and Rydberg atoms. By exciting Rydberg atoms that are inside of a Bose-Einstein condensate, the BEC atoms can now fill in the gap in between the nucleus and the electron. In theory, hundreds of these BEC atoms could exist in between this electron and nucleus spin, and we can see that this happens by small perturbations to the energy levels of the electron itself. This is also a relatively new state of matter and was only observed in 2018. Now let's move on to some more unique states of matter that don't have a strong grouping. The first is a state of matter that's actually a form of magnetism, and that is a quantum spin liquid. And this is a state of matter that's actually defined by its disorder. If you have an antiferromagnetic material, what this means is that the spins that are adjacent to each other want to point in opposite directions. Well, when you put this into a triangular lattice, you have an issue. The requirement of the adjacent atom being pointing in the opposite direction can no longer be fulfilled. And this results in having a series of different ground states of the system that can all have the same amount of energy. As a consequence, the spins are constantly oscillating and switching between which ones are held in place and which ones are not. This is because all of these different energy states have the exact same energy, i.e. that they're ground states of the system. And it is this disorder which makes this state unique. It's called a spin liquid because the disordered spins kind of act like a liquid themselves, ebbing and flowing throughout the system. The next state of matter sounds like it's something out of a science fiction movie. Photonic matter, or photonic molecules, and it could be something compared to a lightsaber. This is a state of matter that is actually quite difficult to produce, and is only formed when two photons are strongly interacting with each other. So strongly that they behave as if they have mass. To form this state of matter, you need to put two photons into an ultra-cold gas right next to each other. In the right conditions, when one of the photons is absorbed, the other photon effectively waits for this photon to be emitted, so then it can be absorbed by the same atom. In this fashion, the two photons push and pull each other through the ultra-cold gas. In this way, they kind of act like a molecule. While this is a rather exotic state of matter, it's possible that this might have some applications to quantum information in the future. Either way, it's certainly a fun state of matter to investigate. Next is a quantum spin Hall state, which is a state of matter that forms in two-dimensional materials. This state of matter has currents that form on the edges of the material, but these currents aren't from electron charges that are moving, but from electron spins. For example, having spin-up electrons moving clockwise through the material, while spin-down electrons move anti-clockwise. As these currents only form on the edges of the material, this can be considered a topological state of matter. This state of matter and other topological systems is a really hot field of science right now. So it's possible we will in fact find more states of matter that are confined to two-dimensional materials. The next state of matter is time crystals. This is an extremely unique state of matter, and while it has been observed experimentally in several systems, it was only theoretically proposed in 2012. This state of matter is defined by the formation of a crystal in time rather than space, where a crystal is just a periodic lattice. Importantly, this state of matter needs to be the ground state of the system, which means that the movement through time doesn't cost any energy. To say this another way, the same system that would be static through time would have a higher energy state than the state that is moving. This is somewhat counterintuitive to everything that we understand about entropy, and thus this is an extremely interesting state of matter to investigate. The next state of matter is superionic water, which is a very difficult state of matter to create. Superionic water requires both extreme pressure and extreme temperature. It is characterized by being an ion conductor, meaning that it conducts using ions rather than electrons or holes. While we call this water, it's actually a form of ice. To form superionic water, scientists took water and compressed it to around 2.5 gigapascals, and this forms what is called type 7 ice. They took this ice and then blasted with a laser to heat the ice up to temperatures that are close to that of the surface of the sun. And this is where this unique state of matter is formed. Under these conditions, the oxygen atoms start to form a lattice, while the hydrogen atoms donate their electron to the oxygen so that the oxygen can form this lattice and then move around freely. In this fashion, the hydrogen atoms start to act like electrons in conductors, and thus we can have ionic conduction. Not only can we actually make this state of matter, but we theorize that this state of matter could exist inside some ice giant planets and could help us to understand the formation of these giant worlds. The next state of matter is a super Tonks Girardeau gas. Again, this is a state of matter that requires quite a bit of effort to produce, and this involves a one-dimensional quantum gas. The state of matter itself is a one-dimensional quantum gas that's extremely resistant to change. Normally, when a gas is put under pressure, it will collapse to a smaller region. But what's unique about this one-dimensional quantum gas is that under these conditions, it doesn't. It seems nearly impervious to pressure, at least to the levels that we've been able to test it to. And this is quite a mean feat, because to create a one-dimensional system can be quite difficult. But to make one that's extremely stable, that's quite an amazing feat. This rounds out the states of matter that we've been able to confirm. There are also many proposed states of matter that we haven't been able to form in labs. For example, degenerate matter. We theorize inside neutron stars that there could be all forms of different degenerate matter. There could be all different types of degenerate matter: electrons, protons, neutrons, even quarks. There are other states that I haven't discussed, such as intermediate states, or even more proposed states. But maybe this is a topic for another video. But if your thirst for states of matter still hasn't been quenched, you can check out this video here where I discuss superfluids in more detail. Thanks for watching, have fun, and see you next time.